Hi everyone, welcome back. Today we're going to talk about the pre-lecture for Chapter 22.
Part 2.
Today we're going to be talking about the chi-square test for independence. So I know last time we already talked about the chi-square test for goodness of fit, but now we're going to talk about the test for independence, which is a little bit different. So with the chi-square test for independence, basically what we have going on is you have two variables with two or more categories each.
But what are we even testing here? So we need to write down our null and alternative hypothesis. So I always think it's easier to go ahead and do an example just to illustrate what we're trying to do. So we have an example here. Marie, can you let everyone know the context of the example?
Of course. So this example problem says, a simple random pool of 300 Americans, with 150 being 18 to 35-year-olds and another 150 being 36 and older, were asked the following question: do you think the benefits of social networking or social media usage outweigh the risks? And basically there were three possible responses. They could say yes, no, or unsure.
Okay, so it looks like we definitely have two categories going on here. We have the response, which Marie just said yes, no, and unsure, and then we have the age group of people. So again, two variables, two or more categories, and what our null hypothesis would be is chi-square test for independence. The name kind of gives it away. We would say that age is independent of their response to this question about how they feel about social media.
So now we have our null and alternative hypotheses written out, and basically what it sums up to is that the age and opinion of social network or media is independent of one another, meaning that the differences are just due to chance. Whereas for the alternative hypothesis, it's a little more interesting, and it says that these differences are these variables are dependent, making the differences too large just to be due to chance.
So these, as you guys can see, the null and alternative hypothesis are really relatively the same thing for all of the hypothesis testing. Basically the null is dull and that whatever we see, whatever difference is just due to chance, and the alternative is that the difference is too big to be due to chance. So basically, as Rachel just said, the null and alternative hypothesis for the chi-square test for independence is exactly the same as all of the null and alternative hypotheses for the other tests.
Alright, so now that we have our null hypothesis and alternative hypothesis decided, now we'll look at the observed and expected frequencies. So right here we have the observed frequencies given, and they're always going to be provided to you no matter what. And basically the chi-square test statistic is the same for the goodness of fit model as it is for the independence test. You will do the chi-square equals the sum of the observed minus expected frequencies squared divided by expected. So you're going to use this same formula again, and now we're going to calculate the expected frequencies with the observed ones, but we're going to do it a little bit differently this time.
Okay, so we can get the expected value by looking at the formula, which is expected value equals row total times column total, all over the overall total.
Thank you, Rachel. Okay, so now that we have this nice easy formula, there's another way to do this which will be explained in class, but the formula is definitely the easiest. So what do we mean? Well, we're going to use what we're given. We're going to look at the observed frequencies. And say I wanted to fill in this cell right here. The people who answered yes who are between 18 and 35 years old. Well, I take the row total, so I go all the way over. Here's the cell I'm looking at. I go all the way over. The row total looks like it's 150. Times the column total for this cell is 93. Divided by the overall total is always the number right over here, so that's 300. And then I would solve this, and that would give me my expected frequency for this cell. Let's say I wanted to do another cell. What about the people who answered no, who are 36 years old and older? looking over here, that is this cell. So Rachel, what's my row total?
150.
150. Row total times column total. What's my column total?
99.
99 divided by my overall total never changes. It's always going to be 300. And we do the exact same thing for all of these other cells. Okay, so after using that formula, we calculated all of our expected frequencies as shown in this table. And you guys can see, it's not surprising. These expected frequencies are based on the null, based on the idea that age and response are independent. So regardless of their age, we have the same amount of people that we'd expect for yeses, same amount of people for nos, and same amount of people for unsures.
Alright, so now that we have our expected frequencies and our observed frequencies, we can calculate the chi-square test statistic. So in order to do that, we're going to use the formula that we discussed earlier. It'll be observed minus expected squared divided by the expected. So for the first one, we would do 71 minus 46.5 with all that squared and then dividing by 46.5. And then we will do it for the second one, so it would be 33 minus 49.5 with all that squared and then divided by 49.5.
And we're going to keep adding every single box together and getting each of those individual chi-squares, add them together until we get our last one, which is
62 minus 54 squared divided by 54.
So then after we add up all of these, we'll actually have just one variable or number for the chi-square. So now we have a value for chi-square, which is 39.2, but we can't yet say whether or not we can accept or reject the null.
So the last thing we need to do is calculate the degrees of freedom. So for the chi-square test of independence, the degrees of freedom is going to be the number of rows minus 1 times the number of columns minus 1. And in this case, we have 2 rows and we have 3 columns. So basically we're going to do 2 minus 1 and then we're going to multiply that by 3 minus 1. And we will get a grand total of 2. Alright, so now that we have the chi-square test statistic and we have the degrees of freedom, we need to find the p-value. So when you go on the chart and you look up where these numbers fall, you end up getting a p-value of less than 1%, which means that you would reject the null and you would accept the alternative hypothesis, which would mean that the differences between the observed and expected frequencies are too large to be due to chance, and the results are statistically significant.
Wait, am I supposed to say it? Was I exactly are we testing? And I always think
So now we have our null and alternative hypotheses written out, and it looks like age and opinion based on social media, they're independent of one another, which means that basically because it's dull, that everything that we see is just due to
chains? Oh no! Carly, you need to check yourself before you wreck yourself. Oh no! This is not how you spell chance. Sorry, guys. Sorry. Alright. Okay. Alright, so in other words, the null hypothesis is pretty much the same. We're still going. Why am I still going? I gotta keep going. Okay, so pretty much,
So now we have our null and alternative hypotheses written out, and basically what it sums up to is that the age and opinion on social...
Alright!
Should I just step off to the side?
Also.
And if you would like a tutorial about the headband braid, please click here. Alright! Okay, so to calculate our chi-square statistic. No, wait, I just remember we need to say something else. Can you actually stop? Okay, should I just go? Okay, so I remember what we need to say. I remember what we need to say.
So the first one is expected value equals row times column all over.
Is this wrong? Alright! 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 So, for one true false question.
Am I supposed to say something?
Actually, we should go over that.